like to give you a little bit of background. I do work a lot on business cases, and I provide advice on how to build a system for either general purpose computing for, HPC, or sometimes for very, very specific applications. Okay? And because it's a business, so the customer may look for different solutions. So when you're trying to give advice, you should really know not only your own product or technology, but you really need to be very knowledgeable and respectful for competitor technologies. And this seems like an obvious thing, but doing your homework is a big task. Okay? So you really need to understand other CPUs as much as possible, the systems, the networking technologies, nowadays also accelerators, nowadays storage solutions, nowadays networking just keep growing, and it never gets easier, it just gets more complicated. So what I want to do here is, all right, so I want to give you my personal view. So these views and statements that I'm going to be showing here, it's just my own interpretation of things. I think that people would certainly, hopefully, value that rather than just kind of doing a marketing bullshit presentation of somebody like some company. Okay, so while I'm currently working for HuaweiI, I'm just telling you here what I think. All right, and you're gonna see that I am not biased whatsoever across about a certain particular architecture. And we're gonna talk a little bit about multiple architectures, and at the end I have like few slides that says what I think about this particular architecture, whether it's good, what I think what is good on another and another and another, and then I say what I think is bad on each of them as well. So you can find really good things or strengths and bad things like weaknesses. And obviously, unless you have a very, very particular workload, then you can be very specific in terms of what architecture makes sense. But a lot of people has to run a wide range of applications, which basically means that there's no perfect solution. Okay? So the only thing I want you to realize is the trade-offs. That's basically what I'm trying to do. Okay? And I want to explain you also some issues, some weaknesses, or some issues, some challenges that I see on current architectures. It doesn't matter which architecture you pick up. And then the upcoming needs. And some architectures are handling things well, some are not. And I want to give you a little bit of insight of some of those issues that are happening, and then you're going to see some evolution, and it's because of what we're going to be discussing in here. So I just want you to kind of get some thinking in terms of issues that are happening. And because I may say, oh, this is good, this architecture is very good, I can also come with a lot of cases why that architecture is not good, and you can do that exercise as well. So when I meant here corner cases, it means you can always find bad cases for a particular architecture when I had said, oh, this architecture looks good. Okay? Also, I don't want to brainwash anybody. This is just my opinion. So I don't want you to take this as, okay, this is a guide about how to purchase systems. No, I don't want to do that. The only thing I want is to kind of give you my perspective, my personal view on different architectures. Okay? All right. Let's move on. Okay, so this is one of those systems. They got IBM Power, they got the Intel Knights, and then also they got ARM. So I do obviously have my own agenda. Basically, I have my own data points I want to put in here. So there's certain things that I really want to make sure that I get into your head, which is basically to make you fully aware that there is more than just Intel solutions out there. Okay, that perhaps is my main point. Okay? I'm not going to say which one is best because there is nothing perfect, but I want to make sure that there is more than just Intel solutions. Okay? And here you got a good example of that. You got IBM Power architecture, you got the Intel accelerators in there, and also you have ARM. Okay. This is two other supercomputer systems. Another one, that's with IBM Power also. It's just a coincidence, it happens to be again IBM. I mean, I wasn't picking up, like I'm not promoting here an IBM solution. And then this is an ARM solution as well. But just kind of, most of the people is actually running Intel-based servers, right? So here you can see other solutions that are non-Intel-based. So that's the main point I'm trying to make. Most likely at the supercomputing now in June here in Frankfurt, they're going to be making a lot of noise about these two systems, and they have different features, each of them. ARM certainly is going to be talking a lot about this, and Intel certainly, because they have a lot of the market, they're going to be starting to kind of do their own analysis as well to find out, oh, how damn good is ARM, All right. So this is just a table that kind of summarizes what are the server CPUs that you can actually go now buy. Okay? I will say that, are we recording also voice or not? Oh, we are? Okay, I should be careful with what I say then.
If you want, we can read.
No, that's okay, I'll be careful. So this is something that you can go buy, okay? So you can see there's nothing from Huawei in here, okay? That's why I need to be careful what I say. But certainly we're doing our own thing as well. All right, and then you can go buy these ones. I'm not gonna go into the details of this right now, but anyway, you can go buy these things. Okay, so this is just some pictures. This is not a picture of the CPU, but it's like a block diagram that shows how the CPU is architected. The Thunder X2, it's an ARM-based. Down here, you got the Intel from a Skylake. This thing is an EPIC CPU. So these are the CPUs. For this one, I really know about it. So this is one CPU and then another chip. So these are what we call a multiple chip model. And then this is the IBM architecture, and then you got this core. So what we have, also you can see this group of 4. So they call them like core clusters. And this is a very important from the perspective of how you get to manufacture these things, how you get to put many cores in there. Okay, so everybody has their own strategy, and when you pick up strategy, there's going to be some strengths and some weaknesses, and we're going to talk about some of those things. Okay. All right. So this is just a subset, so a small set of micro benchmarks that for the people that is into the HPC, you should really know very well. Okay. It's just a subset, there is many more. But these are kind of fundamental. I mean, you can cover a lot with these benchmarks. And it allows you to do a lot of comparison between core architectures and CPU architectures and system architectures all the way to the rack, especially when we're dealing with things like LatePath or the high performance conjugate gradient benchmark, which we'll talk a little bit about this. Okay. This is just an example of some work that I did in the past. This is all public information, so there's no issues with this. But this is just an example, a way of representing information where you got like features and then performance, and then you kind of put it in a TVA chart, and then you can see like this is your baseline, and this is okay, 60% more cores, so many PCIe, so much memory channels, which translates into some memory capacity, which translates also into some memory bandwidth as well, PC bandwidth. So it's just one way of representing information, okay? And then you can put a bunch of architectures in here to compare and so on. And when I did a presentation of this one, I call this one like the elevator pitch. And the elevator pitch is basically means you got say 20 to 30 seconds in an elevator with somebody that you want to brainwash about this particular architecture, why it's better than another one. So it's just one way of representing information. Okay, so let's get a little bit, it's a lot of information I need to cover, but I'm going to try to go a little bit quick. How much time I have?
Half an hour total, 25 minutes, 20 now.
So, okay, about 20 now. From now, 20, okay.
Between 20 and 25, yeah, depends.
Okay, all right. So the first line says multiple logical cores per physical core. So you can find architectures that are single core, and some architectures have this hyper-threading. Other technologies call it symmetric multiprocessing. Everybody comes with their own fancy name, but it's basically this kind of multiple logical cores, which definitely they get to share the same units. So there's not a lot of scalability that you can get, of the real core, unless you are very careful about what threads or processes you are placing in that place, making sure that you are not using too much from one on the other because they are kind of stealing the resources from each other, okay? So when you hear, oh, this guy has, say, up to 4 SMT, like IBM, well, you have to make sure that, I mean, there's going to be a bunch of resources that are a single one, and then you just kind of have the illusion that there are many cores in there, but they're going to be all competing for the same resource. Okay, so you have to be careful of this. Again, you're going to have to do a lot of runs by yourself on your own micro benchmarks or your own applications to find out whether these are scales or not. But this is the way that they are trying to come up with better utilization of the resources. Okay, then you got different cache hierarchies, like you got L1, which is usually 1 per core. Then you got L2, also per core. Sometimes it's a shared one. Nowadays, most of them are independent L2. For sure, you usually have an L3 or that last level cache that is shared. Well, so if that resource is shared, usually one of the challenges you're going to run is, so imagine here you got this core cluster thing, and then you got one core which has their own L1 and L2, and then you got like a shared L3. So imagine all of these guys want to get some data, and you got this one in the middle. So this could become your choking point. Okay, so then also manufacturing-wise, you have challenges in terms of yield. To make sure that all of these cores, say 28 cores in a single block, they are all healthy. Sometimes you can't make all of those many cores manufactured properly to be healthy. Okay, then what we're going to do is that we're going to build smaller chunks, and then and this is like a die, and it's easy, it's very easy to get 4 healthy cores, and then when we put another one and another one, now we need to connect them, so we will have to connect them with a coherent fabric, which will add some latencies and some bandwidth challenges. So here you got some trade-offs going on already, okay? All right. Another area where we're going to talk a little bit is on the memory channels for memory controller. This is an area that I think it's a very obvious one that I want you to pay attention. So let me just show you here. Let me see. Here is a battle. I call it a battle for the memory bandwidth. So this is also a chart that shows only AMD against the Intel, but I want to give some information here that both ARM and IBM are also in this battle. So what I wanted to show you here is that, okay, you remember in this first picture, here. So on this line you got 8 memory channels for the Thunder X2, so that's an ARM, 8 channels. You got 6 channels on the Intel, 8 channels on the AMD, and 8 channels for the Power. So and also here you can see frequencies at which they are running. So this is once all the cores are trying to get data, eventually they have to get it from the memory controller. So for example, if I go to that chart in here, this is the bandwidth in gigabytes per second that every core is capable of getting. When I have one core running only, or 2 at the same time, 4 at the same time, 8. So what happens is that, for example, for something like this, so all of them have to go through this thing. So it basically means that did you lose the audio? Or are we okay? So it means that everybody has to go through the same thing, so they have to share the bandwidth across all the cores. So you can see that in here, like on the Intel, it starts dropping the bandwidth. Like it's capable of sustaining like up to 2 cores with a constant bandwidth, but then the 4th one is already starting to drop the bandwidth because you have to share it across all the cores. So then basically your 4 cores at 16, you're already maxing out the 6 memory channel. On the case of the EPIC, for example, in the case of EPIC, in that picture in here, so this is a CPU. Then you got these cores have their own independent memory controller. These ones have their own independent memory controller, and so on. So I can have one core running in here, getting access to the memory, completely independent of this one, completely independent of this one. So they got their own dedicated bandwidth. Okay. So that's what you can see in here, like this flat line in here for 1 core, 2 cores, and 4 cores. Okay.
So this is a 6 memory channel. This is one core running 2 memory channels. This is another core, 2 memory channels. So this area is actually very important. And what I say here is true also. The ARM CPUs and the IBM have similar performance to the AMD. So it's very important. So why this area is circulated? It's very important because imagine a really expensive commercial software that they are charging you on memory bandwidth per core. So what you want is to run the application with the fewest amount of cores, because they're going to charge you, say, $5,000 per core. So if I have to run that commercial application, I need to get the best performance per core. So out of the CPU, I will just run, say, with 4 cores or up to 8 cores, and say up to 8 cores, the ratio of bandwidth per core is up to 50%, which basically means that, okay, my hardware is, say, $15,000, but my license is, say, $100,000. So it's worth them to run on something like this let me call it this way, 8 memory channel thing. I don't care whether it's the AMD or the ARM or the IBM, but if they can offer me better bandwidth per core for few cores, then I'll use that kind of CPU. Okay? And then once you pass that point of every core having their own independent memory controller, then you start sharing the bandwidth so that it goes down. But you can see here that it sustains that bandwidth difference by a factor of 30%. And the reason why it's about 30% is because you got 8 memory channels versus 6 memory channels, so that's about 30% difference. Okay? So everybody is now pushing into 8 memory channel. You're going to see a lot of advertisements in there. ARM or IBM is 30% better than Intel. The reason is because they got 8 memory channels versus 6 memory channels. And Intel saying, holy shit, what do we do? Okay, let's go on do an 8 memory channel as well. It's going to take its own time, all right? Now Intel did realize what it is, and then they just rolled their sleeves and said, we better do a lot of good optimizations on the software to try to compensate the lack of bandwidth. So actually that's something I got here in this one. You guys are very familiar with Limpa, which is all about flops, the CMD bandwidth, and core frequency, and lots of cores. But you really need enough memory bandwidth to feed all those cores. So imagine they got, say, the 8180, which is 28 cores, and you have 6 memory channels. If you do a memory bandwidth analysis when you're running Limpa, it is right there. I mean, you're running also AVX 512, which then consumes more bandwidth rather than 256. So it's properly architected to consume that kind of level of bandwidth and get linear scaling across all of those many cores. But if those cores were running at higher core frequency, because AVX 512 dropped the frequency, or if you were running if you did not support memories DDR4 2667, then you will see a poorer scaling of the performance. So then they would not be able to offer you a 28 core, they would have to go lower because it's not good, for performance reasons and marketing reasons also to show lack of scaling with so many cores, okay? Okay, if we go into the high performance conjugate gradient, it's a different benchmark, okay? It's all about system I/O. It's not only the memory bandwidth, it's also the connectivity between the 2 CPUs or multiple CPUs. And the guys at Intel, they've done a really, really good job in terms of software optimizations, applying the techniques that I mentioned here. So they do memory bandwidth reduction. That's kind of the marketing or technical term that they're using, but at the end, it's trying to do some caching, and then you got 2 computational kernels that you put them together. So you kind of, once I got the data in for one kernel, then I use it for the other kernel as well. So that's fusing kernels. And then putting data in a continuous manner so the hardware prefetcher can bring data quicker. And I think that's important because this is a sparse linear algebra. So a lot of times it's kind of pointer chasing, so it's like very random. So that's not good. I want to show you something here for this other benchmark. This is local and remote memory latencies for this benchmark in here. This is the LM bench, the latency memory read. So here you can see in this one here, I think this was an old Intel architecture, but it's clearer than this one. This was done by Anantech. But this is L1 cache latency, L2 cache latency, L3 cache latency. And then once you run out of your last level cache, then it will go to main memory. And then you separate between local memory accesses versus remote memory accesses, and it's a big jump. But this is kind of random accesses. If data is access continuously. You know, like you got an array and then you're just accessing one point, and then the very next, and then the very next. The hardware figures out your access pattern, and then it just comes to prefetch data directly without needing any software prefetcher, things like that. So then all your latencies, they go down to this level. So that's really what you get in terms of hardware, thanks to the hardware prefetcher, even if you're using data that it's outside of your cache. Okay. So this is very important to reduce drastically your latencies. And also another interesting thing related with this is, here, let's look into this connectivity between the CPUs, because, well, you want not only scaling capability or performance in one CPU, but also how you build a multi-CPU into the same node. So for example, cores in this CPU, then you need to access this other one, or you need to go through this coherent interconnect to go to this one, or even jump to the other one. So this will actually increase even more your latencies. And then when you have like a database application, you know, you need uniform memory access, whether the access is local or remote. You want the remotes to be, especially if you have locks. So if the lock says, okay, I need this other core over there just to look at the same data over here, then these cores local here, they just have to wait until the remote ones are done with their work. So then they're slowed down quite a bit. And that's because of the drastic difference of local versus remote memory access. So ideally, you would want uniform memory access everywhere. And that was like the front side bus that Intel had, say, 10 years ago. But now, in order to provide from a manufacturing capability, scalability, then you need to create independent ones. But now you have to make your software NUMA aware, local accesses. So it's become more complicated. But one thing I want you to realize is, for example, this is an AMD platform. That's how you're putting a lot of cores. So in this case, 64 cores. Now here, you just got 2 guys, which basically means 50% of your access are going to be local for the cores in here, and then those cores in here, they would do 50% of accesses that are remote if you had no control whatsoever of accesses. But on something like this, only 1/8 would be local, which is about 12% of local access, and everything else, like 87% of the access, would be remote. You know, and for HPC applications, you do have control, but there is a lot of enterprise applications that you don't have control. You know, like you come a request coming from the network, you want from a key value store a data point, and then that data point is not necessarily stored locally into the memory pool that is controlled by the process that was handling the request. You know, it could be the process handling the request over here, but then the memory is being on the other place, and then you get a lot of traffic going on through the coherent fabric as well. So that's another issue. Here you got, say, those 3 links of UPI in this case, then you got 2 links in here, but any link can get access to everything, and any link can get access to everything. This one is a different animal. This link in here can only directly access to this one, but it cannot access the others. So then you have to, so theoretically, the aggregated bandwidth, here's like the marketing guy say, oh, how much bandwidth I have between these 2 CPUs? Well, in this case, and in this case, you know, you can easily aggregate them, but because one process can access the whole thing, and if you need more bandwidth, you use another one and use another one. But in this one, you can't aggregate this unless you do it explicitly. Like you have to have this process, a process right here talking to this one, a process right here talking to the other one. But if you want like an all-to-all, it's very complicated to do in that kind of platform. Okay, so it's nice from the way that it's easy to manufacture and build something big, but it's really challenging from a programming perspective to exploit the capabilities of that platform. So again, I'm not going to make you happy saying, no, go this way. You know, it's good and bad everywhere. Okay. All right, I talked about this, I talked about this one. All right, this is another interesting thing coming up. PCIe devices. So it's growing like crazy, right? So 40 lanes, 48 lanes, 128 lanes. So you got a device in there, and then you're gonna pump data from the CPU into the device, or from the device into the CPU. You better also have a very powerful memory controller to move all that data, right? So that's why you want memory bandwidth as well, so you can read or write into those PCIe devices. Okay. Now you may want to use, for example, only one core to try to access a very, very fast device. So we're moving from PCIe Gen 2 to PCIe Gen 3, from PCIe Gen 3 to PCIe Gen 4 this coming year. So, for example, and you have 4 lanes, 8 lanes, 16 lanes. So, okay, I got here something like This is Gen 3, it's hard to read from there, but this is Gen 3, 16 lanes. This is Gen 4, 16 lanes. So this is 100 gigabits per second, about 13 gigabytes per second one way, 26 gigabytes per second both ways. That's this guy. If we go into PCIe Gen 4, it's 2x that. So we're talking, say, 25, 26 gigabytes per second one way, 25, 26 gigabytes per second the other way. Now let's look into this chart in here. This is the bandwidth that one core can get. So we're talking, say, 20 to 25 gigabytes per second. So that basically means that I can do a read from memory controller and then also a write at the same time, and then my aggregated bandwidth is in the range of 20, okay, let's be general, say 20 to 25 gigabytes per second. If I have a PCIe Gen 3 by 16 device, I can do, say, 13 in one direction, 13 in the other, it's 26 gigabytes per second. So one core only can handle one PCIe device Gen 3 16 lanes. But we're introducing PCIe Gen 4 by 16. How the hell are you going to handle with just one core, say 56 gigabytes per second bidirectional? There's no way. Cores are not that fast. Okay? So what are we doing? Oh, then when we're pushing with one core, you're not going to fully saturate the bandwidth of that PCIe device. Well, we should use more cores then. Yeah, obviously, you got no choices. But also, you have the following here. Okay, yeah, this is a good chart. So this is a current thing. This is what's coming up. All of this information is public, so I'm not bringing in something confidential here. So imagine you got your device. So, okay, PCIe Gen 3 with only one core here, it's okay. Now also I have my InfiniBand device in here, my GPU, and I want to access it from this other CPU. How are you going to access? Oh, it's going to have to go through this. Oh, well, but this you were using it for connectivity between these two for coherency. Now I'm going to have to share this thing for also the access to this device. So, because these devices are becoming very, very powerful, then you're starting to eat a lot of the bandwidth that you used to design these two CPUs for fitting this device. So this is not good, you know, because this is going to become a choking point. You know, these guys can access it well, but these guys can't. Okay? It offers also different levels of latency. So this is a solution where the PCIe Gen 4 device, 8 lanes out of the 16 go directly into one CPU, and then the other 8 lanes, they go into the other CPU. So why would you do this? Well, so I think there's 2 reasons, right? And I already mentioned it. One is that if I just want to use one core, at least with one core, I will be able to fully saturate Gen 4 by 8. I will not be able to saturate by 16 Gen 4. So then I'm forced to use another core to fully saturate the device. But when I'm doing that also, then I'm not using this link. So I'm releasing this one, and I'll just have it used between remote memory access between these two, but I will not be taxing that link because of PCIe accesses. Which then is forcing you from a software perspective to say, if I want to use the device, now I need 2 processes, and then you're going to be on different guys. It's like a multi-rail thing, but in the same system. So this is like it's called a multi-host. So you're going to, and by the way, this is just one example using InfiniBand, but you're going to see this also with NVMEs as well. So you have a collection of NVMEs, and then you're going to see this dual controller thing going from one device and the other, and you have to make them NUMA aware and all that thing. So again, things are becoming more challenging from a software perspective as well. But the main point I want to make is that those PCIe devices are going faster, faster, and faster. Okay? Another interesting thing I mentioned here in the single core performance is this last line that talks about interrupt handling for the PCIe devices and moving into user space versus the kernel mode drivers. This is very important because those PCIe devices are so fast that when the core wants something, then okay, the device issues an interrupt. Hey, I'm done. Please go get the data. And then you issue another one. I'm done. And then you have to have a core fully dedicated to handle that device. Well, you wish it was just one core, because it's actually starting to use 2 cores, 3 cores, 4 cores, just for one NVMe device. Now you're saying, oh, I got a lot of PCIe lanes, which I can put a lot of PCIe devices like NVMEs, say 12 NVMEs or 24 NVMEs. In a 2U, you can put up to 24 NVMEs. I mean, you can go and look into one of these systems that has many NVMEs, and you can do a scaling study. like say 1 core or 2 cores to fully utilize one. I mean, you want to actually make sure that you're fully utilizing that NVMe device because it's really, really expensive. It's actually more expensive, like I say, 3.2 terabyte NVMe. It's say $5 grand, you know, something like that. It's even more expensive than the CPU, and you're putting 24 of those. So out of the say 60 grand system, you know, about 40 grand of the system goes to just the NVMEs. So you better make sure you're dedicating enough cores to the handling of those very expensive devices. Okay, I'm almost done. Okay, so some of these CPUs, or almost all the CPUs, it's already well understood that some workloads, you know, it's not enough. You want to pair it with an accelerator. And the accelerator could be a GPU for general purpose. It can be an FPGA for which is reconfigurable. And then you can get an ASIC, which is even more restricted purpose, like the tensor processor. And obviously, you don't just put one, you put many of those. And then you have your own topology for the connectivity between them, okay? And then you can have different topologies like ring or fully connected. And then you have to come up, I didn't put it in this slide, but now you need to have your own software stack for handling that particular topology of the accelerator, okay? Like for example, if you're doing MPIs, collectives, now you need to be making topology aware. Obviously, the hardware vendors are trying to provide that level of software optimization that you're plugging in with the MPI, for example, for those collective accelerations. Here you can see 2 examples. So do 2 Intel CPUs, and then this is doesn't say what CPU it is, but then you can see a group of GPUs with the NVLink in here, another group, and they are physically connected to this end. So this is kind of like a hub where you're connecting the accelerators, but you're almost not using them. And then you have them talking. The only way that you go to this guy sometimes is because you need to get the data out of this compute node and then go to another one through InfiniBand, for example. Here you've got another case using a different protocol, C6, which is the processor, and then you've got the FPGAs in here, and then they're connected also in this approach. But some of these designs, they've got a lot of connectivity, and in fact, you can actually get rid of the networking and just connect one compute node to another over this kind of connectivity. So you don't need the regular networking as long as you know very, very well your I/O pattern, okay? So you can build very scalable systems with those accelerators. And the processor, it's not useless, but it's almost useless. Okay. Finally, on the CPU power consumption, you got, like my experience I've seen is like, you get a power budget for your team, and then there's another team that builds their own subsystem, you got their own power budget and so on. So the total power budget is kind of the maximum amount that you're going to be able to cool. And then people may want to compete for more power consumption, so then I can get higher performance for my particular subsystem. But at the end, you know, it's a company building a single product, so you have to make sure that, you know, you don't steal much power from the others. But this basically is kind of separated between core power and core power. There's a lot of research going on also in terms of dynamic core frequencies. I wrote down uncontrolled and workload dependent because you really don't have, as an application developer, the insight in terms of how the power credits are being used. So usually, a lot of the performance optimizations that you're trying to do may have data, for example, staying longer time into a particular cache, which then will consume more power consumption. So instead, while caching is good for performance, it may burn more power, which will trigger you to go to a lower core frequency, which will reduce your performance. So you did a caching optimization, but reduce the performance, not because of the caching value, but because of the power consumption, it's kicking in, and then it's going to reduce your core frequency, which is going to hurt your performance. And here you can see different levels of CPUs, up to even 250 watts. Okay? And then these are nodal power, so it goes all the way down from 350 to 600 watts. I can tell you that with some companies that have been working in the cloud computing space, what they're doing is say, okay, I got, say, 1,000 workloads, and then every workload, when I run it, it gives me some amount of money. So obviously the performance, it's somewhat important. And then what they're doing is with the node kind of reducing the power consumption, would reduce the frequency, and then you know, the return of investment, you know, it's unaffected by reducing the power consumption. But at some point, it's when workload starts running too slow, and then it starts affecting your business. So that's the optimal point of utilization, because at the end, what you're doing as a cloud provider is just paying an electric bill, and then you're just getting as a return investment, the execution of those workloads. So it's very important, that don't think that, oh, I'll run at the highest power consumption, because it will run at highest core frequency, and then that's where I will get the highest amount of performance, and then workloads being executed. No, it's not like that. It's non-linear, and you have to study this. So people cares about how much money I can get by having the lowest power consumption or the lowest bill. Okay, so these are different architectures, and then kind of this is like final slides of conclusion. What do I think about the Intel, which is most of the market, right? So I think that the software ecosystem is very mature. Applications are ready. So they make sure that when you're buying a system, applications are running well. Same with the hardware ecosystem. It's very mature. You've got lots of options, flexibility, and so on. So that's why most of the people goes with this, right? You've got also very good or competitive core performance, and a lot of that value is because the hardware prefetch is really good, but also they got very competitive development tool chain that is able to exploit vectorization. Okay, so you must understand it's not only about the hardware. You have to have really, really good software, and they got very good power consumption. Okay, very good control boost. Another important thing is they put as many cores as they can into the single memory node. So then it makes it very good in terms of local memory access and remote memory access, and very competitive remote memory bandwidth as well. They got proper balance between local and remote bandwidth. Okay, so this is what I think in terms of positives of Intel. In terms of positives of AMD, I think that AMD is leveraging also most of the code that Intel has done, but not all. That's why I say most, not all. Okay. So then the number of platforms is coming back. We've got many hardware vendors developing platforms now, so you're hearing more about this. But also it means that it's not all there. It's still growing. Okay. So maybe there is an option that you're looking for. It may not be available in there. Okay. But there's a lot of development going on. The hardware vendors are kind of sensing the market. Is it good enough? Let's go make more platforms. Okay, so one of the main assets is the game memory channels that provides you 30% more performance uplift. But remember what I told you about the Intel, while it's 6 memory channels, they're doing a lot of work on the software side, so they're able to close the gap. So AMD actually is not doing that kind of work, which means that yes, brute force you can get more, but if Intel is able to close the gap, then where is your value? So you have to actually do the same software optimizations to keep that distance. Okay? One of the key areas is it has a lot of PCIe lanes, so then you can throw in there a lot of PCIe devices, so it's better and cheaper in terms of designing a platform with a lot of GPUs or a lot of NPUs in there. And it has a lot of core count in there, obviously the pricing. But while performance is not negotiable, it is what it is, through optimization, pricing is always negotiable. So you can always lower the price as much as you need, to try to win a deal. All right, ARM. It has also very good core count. Also, the number of platforms is growing. So kind of similar situation to AMD, not quite. Okay, AMD has more platforms already, but ARM is starting to kind of grow. Also, it has those 8 memory channels. The open source software ecosystem is also very mature already, because there are ARM and Linaro as dedicated organizations to push for that. Remember, I'm saying open source, not commercial, so I'll get that later into. And also it has very competitive pricing. In terms of the IBM, competitive core performance, competitive core count, also the memory channels. These are the only ones that they have PCIe Gen 4 ready right now. Okay. They have a very mature software ecosystem, but the reason is because they make sure they cook a turnkey solution. So don't go out there and try to do your own thing, because you're going to have challenges. They offer you the whole thing. So you pay some amount of money, but it's headache less. 2 minutes. Okay. All right, I'm almost done. So cons on the negatives, I would say, on the Intel. Lack of effectiveness of the AVX3 because the core frequency drops too much. I think that the core scaling bandwidth against EPIC, for example, is not that great. On the AMD, the remote memory bandwidth and the latency, it's behind scale, Skylake, so that's not a negative. And then there are other challenges. Getting applications certified on the upcoming platforms, it's taking time, okay? Like if you have to buy a cluster, you have to make sure that all those applications are running well. Otherwise, you're going to have a nice surprise. And then the development tool chain is not that mature yet, so that's another issue, okay? On the ARM side, the latency is behind on against the Skylake. Vectorization capability is also behind against the Skylake. And then this is the other important thing: commercial software offering is not there yet. So that's an important problem. Okay, and again, like AMD, you need to do the application certification on the upcoming platforms, and that takes time. Building us turnkey solutions, not there yet. So it's taking time. A lot of research institutions are doing their own thing because of the open source. So you want to do it all by yourself, yeah? All of this is available, but if you need a real application, commercial application, it's not there. Okay? And then on the power, so it's restricted flexibility on hardware and software. It's kind of vendor blocking, okay? But it's a good and a bad thing. So because of it, then it has a higher TCO, but because it's also you're packaging there also the full set of services. Okay, so I'm done. Any questions?